For the last 100 years or so, physicists have been on this epic quest. They've been trying to find the fundamental rule book for our entire universe. And the crazy thing is, they actually found it. It's called the Standard Model, and it might just be the single most successful scientific theory ever. Seriously.
And look, that's not an exaggeration. We are talking about a single set of rules that governs pretty much everything. I mean, from the light that's hitting your eyes from your screen right now, all the way to the nuclear fusion that's powering the sun. It's all in there. It's all described by this one model. The only major thing it doesn't cover? Yeah, that's gravity.
Okay, so it's obviously a huge deal, right? But what is it really? What are we talking about when we say the Standard Model? Well, that's exactly what we're going to do here. We're going to unpack the core ideas behind this incredible theory piece by piece. Right, so before we can really get a handle on the rulebook, we've got to meet the players in the game. And to do that, we're going to go on a little journey. But we're not heading out into space. No, we're going the other way, inward, deep, deep into the very heart of what everything is made of. It's kind of like peeling back the layers of an onion, but for reality itself. First, we had atoms, right? We thought, okay, that's it, the smallest thing. But nope, we cracked those open and bam, found this dense little nucleus inside. So we zoomed in on that and found it was made of protons and neutrons. But we weren't done yet. We pushed even further, looked inside those, and that's where we finally hit the jackpot, quarks.
And you've got to appreciate the scale we're talking about. I mean, to actually see these quarks, we had to build machines that could probe distances of 10 to the minus 17 centimeters. That number is it's mind-bogglingly small. It's a decimal point with 16 zeros and then a 1. The fact that we can peer that deep into reality is just an absolutely incredible achievement, and it's what proved that quarks really are those fundamental building blocks. Okay, so we've met the players, the quarks, and a few others. Now it's time to learn the rules of the game. And here's the amazing part. It turns out that every single interaction in the entire universe, I mean everything from a little magnet sticking to your fridge to an exploding star, it's all governed by just 4 fundamental forces. That's it, 4. And you can see here just how different they all are. First, you've got the strong force. This one is the absolute heavyweight champion, but it's got short arms, it only works over tiny distances, basically holding the nucleus of an atom together. Then you have electromagnetism, much, much weaker, but it has infinite range. It's the reason atoms and molecules stick together. The weak force is, well, even weaker and has an even shorter range, but it's super important for things like radioactive decay. And then, way down at the bottom, there's gravity. It is ridiculously, almost comically weak compared to the others, but it's the one that runs the show on cosmic scales, pulling together planets, stars, and galaxies. So the big question was, how in the world do you even start to write the rulebook for these new weird forces, like the strong and the weak? Well, in what was just a stroke of absolute genius, they didn't start from scratch. They looked backward. They used a blueprint, an idea from the 19th century, that was based on the one force they already understood really, really well, electromagnetism. But first, that old 19th century blueprint needed a serious 20th century upgrade. See, the old classical idea was that a charged particle was just surrounded by this smooth, continuous field of force. But then quantum mechanics came along and totally changed the game. It said, nope, that's not how it works. The reality is way weirder. Forces aren't a smooth field. They're transmitted by particles literally throwing and catching other little particles, these tiny packets of energy. It's like a game of cosmic catch.
And this right here, this is a picture of that game of catch. It's a famous little drawing called a Feynman diagram. On one side you have a proton, on the other an electron. For them to feel each other, one of them literally throws a particle, in this case a photon, a particle of light, and the other one catches it. That's it. That simple act of exchanging that one particle is the electromagnetic force. Mind-blowing, right?
So now they had it, this brand new quantum blueprint, this powerful idea that forces are just particles being tossed back and forth. This was a whole new way of looking at the universe. And the really big question, the million-dollar question, was, could this work for the other forces too? Could they use the same blueprint to explain everything else? And the answer was yes. This right here is the central genius of the Standard Model. It wasn't some totally new idea pulled out of thin air. The theories that describe the strong and weak forces, they're a direct generalization of the quantum theory of electromagnetism. They are literally built on the exact same foundation. Just look at this. It's perfect. On the left, you've got electromagnetism.
an electron and a proton exchanging a photon. On the right, you've got the strong force, two quarks exchanging something called a gluon. See how similar they look? The players are different, and the ball they're throwing is different, but the fundamental game, that game of catch, is exactly the same.
Which, of course, brings up a really good question. You might be thinking, okay, if it was just a simple generalization, just swapping out a few particles, why on earth did it take another 100 years to figure it all out? That seems like a long time for a simple tweak, right?
Well, yeah. The reason is because it wasn't quite that simple. There was a catch. A huge one, actually. The pictures, the diagrams, they might look the same, but the math hiding underneath them contained this massive, profound new twist, something that made these other forces so much more complicated. And here's the twist. It's a fancy-sounding concept called non-abelian gauge theory, but the basic idea is actually pretty straightforward. Think about it. For electromagnetism, the messenger particle, the photon, is electrically neutral. It's like a postman who doesn't read the mail. But for the strong and weak forces, the messenger particles, like the gluons, do carry the very charge they're communicating. They're not neutral, they're part of the conversation.
And that changes everything. What it means is that gluons can talk to other gluons. The messengers can interact with each other, and that leads to these wild-looking interactions, where you see 3 or even 4 of these force-carrying particles all meeting up at one point. This self-interaction just makes the math explode in complexity compared to electromagnetism. This is what took decades and some of the smartest people on the planet to finally crack.
So, they did it. They built this beautiful, ridiculously complex, but stunningly accurate model of, well, almost everything. The theory was basically built. But that's never the end of the story in physics, is it? So what comes next? What's the final dream?
Well, see, the model wasn't just a neat idea. It was a treasure map. It made a bunch of predictions, basically giving physicists a checklist of new particles to go out and find. And for decades, that's what they did. They ticked them off, one by one. The very last, most elusive piece of that puzzle was the Higgs boson. And when they finally found it in 2012, that was it. The ultimate confirmation, the model worked.
But the story can't end there, because remember that one force we mentioned at the very beginning, the one the standard model doesn't include? Gravity. So the ultimate dream, the real holy grail of physics, a dream that Einstein himself chased for the last 30 years of his life, is to finally bring gravity into the fold, to unify everything into one single theory of total unification. That really is the final frontier of physics, isn't it? The grand quest to write down one single, beautiful, elegant equation that describes every single particle and every single force in the entire cosmos. After a century of just mind-blowing progress, you just have to stop and wonder, are we actually getting close? Is a theory of everything finally truly within our reach?